Today I'll present to you our recent few projects on explainable deep learning for structured data. You can see my screen, right? All right. So I will first start with our project TabNet Attentive Interpretable Tabular Learning. And as June was mentioning, tabular data is one of the most common data types in the addressable AI market across a wide range of industries like finance, healthcare, retail, and so on. But if we look at academic research in AI, it is mostly focusing on image and text data. So structured data research has been underexplored. So with the motivation of can we actually push the deep learning literature in structured data, and can we propose a state-of-the-art model that can also get interpretability capabilities of commonly used models for structured data were the research questions for us. So actually, if you look at most of the use cases in industry for structured data, they are based on both decision trees and some variants of them. So our goal was to not only outperform them, but also mimic their benefits in explainability and other things so that we can actually replace those applications. So why deep learning? So there are multiple motivations to consider deep learning for these problems, and these are mostly common for all data types. So a very important one is potential for better scaling with larger data sets. So typically deep learning models can take advantage of very large data sets and can get much better results in the very large data sets regime. And they have certain advantages in efficiently encoding multiple data types, along with tabular data such as images. They can alleviate the need for feature engineering and can go beyond what data scientists can do. And they have some other additional capabilities like data efficient domain adaptation and generative modeling. And these have been explored for image and text data extensively, and there is a potential with them also for tabular data. And lastly, they are better suited for learning from streaming data. So TabNet architecture we proposed was based on utilizing a sequential attention mechanism to choose which features to reason from for tabular data. So here's the high-level idea. Let's say that our task is income classification, and we have these various numerical and categorical features. So our TabNet architecture looks at these columns and decides which ones could be relevant for that particular sample. For example, some of them are professional occupation related, and some of them are investment related, and so on. And reasons from these groups of relevant features on these, and processes that generates and aggregates information, then passes that information to the next decision step, and so on. And these decision steps are repeatedly applied. So overall, TabNet is an architecture that operates on raw tabular data without any feature preprocessing, and it employs a single architecture and trained with end-to-end gradient descent-based learning. And as I will explain later, it enables two kinds of interpretability, local and global. So local in a sense that for each sample, we know what features are the important ones and how the model uses those features. And the global one is that we know across all the samples which features are the important ones. So here is the more detailed view of the architecture with the canonical neural network building blocks. And as you can see that at each decision steps, we have two fundamental building blocks, attentive transformer and feature transformer. And basically attentive transformer generates the mask for feature selection, and feature transformer applies the deep nonlinear processing on the selected features. And these process representations are used towards aggregate decision, and also it is transferred to the next decision step. And we have different mechanisms in feature selection to control the sparsity that is appropriate for the data set, because we know that for some tabular data sets, there are a lot of redundant features, and for some of them, there are less redundant features. So there's a mechanism in feature selection that allows us to control this inductive bias via parameter. And feature processing is based on decision step dependent and decision step independent layers that are composed of concatenation of linear mapping, normalization, and nonlinearity. On a wide range of academic data sets, we have demonstrated TabNet, and we have shown that it can outperform both neural network architectures and also boosted decision tree variants. And in many cases, TabNet actually achieves a very compact model because of the feature selection capability it has. It can use a small number of parameters in a very effective way, so it doesn't waste its learning capacity on redundant features. And it generally yields a compact model, and it prevents overfitting and generalizes better. Interpretability capability, as I mentioned, is also a very desired outcome of it, because especially the competitors like boosted trees and so on come with convenient interpretability capabilities. So the interpretability of TabNet is based on visualization of the feature selection masks. And here's an example. The left one is on real-world data income classification, and you can see that here we have some very important features like the education and occupation and hours per week that determine someone's income. And this is sample dependent, so the importance depends on who the person is. And we also have some redundant features. And on the right, we have a bit more detailed view of this on this synthetic data set, which is constructed in such a way that only a subset of the features are relevant for the output task. And we can see that TabNet learns this from the data so that it can determine which are the relevant features, and it focuses its learning capacity on these relevant ones for each sample. And beyond supervised learning, we have also demonstrated the capability of TabNet for self-supervised learning. So especially on image and text data, with the growth of very large-scale unlabeled data sets, and with the growth of attention-based models, there are very impressive results with self-supervised learning, and we wanted to generalize these for tabular data as well. And indeed, tabular data sets have some certain structures, and exploiting them could be very valuable. Like, here's an example. For this income classification task, we define a self-supervised task of guessing the missed columns. And we know that there are some certain dependencies between these columns. For example, if someone's occupation is handlers and cleaners, their education level should not be doctorate. Or if someone's relationship is wife, and their gender should not be male, and things like that. So learning these structures in these tabular data sets with this pre-training approach without any dependence on the labels allows having a TabNet encoder that can then be very data efficient for supervised fine-tuning tasks. And this we demonstrated it for the application of semi-supervised learning, and we have shown that for the case that you have a small amount of labeled data and very large amount of unlabeled data, you can actually take advantage of self-supervised learning with TabNet, and you can improve the downstream performance. The next project I would like to discuss is temporal fission transformers for interpretable multi-horizon time series forecasting. So the motivation of this project is pretty similar to TabNet project that I presented, with the main difference that here our focus is time series data beyond tabular data. And time series forecasting is, again, a very common problem in enterprise AI markets, as in finance, healthcare, energy, and so on, many domains. And there are many unique challenges for time series forecasting problems that are common across these problems. So real-world time series data sets consist many types of input features. They have past observed inputs, such as past sales. They have a prior non-future inputs. So these are the time-varying features that we know the values a priori. For example, holiday dates, we know their values before they come. And then there are static features which also affect time-dependent dynamics, such as store location. So if a store is in downtown, for example, it might get more traffic after hours and so on. Then another challenge is that typically only a subset of inputs are relevant, and the remainder can affect the generalization performance of deep neural networks. Then we are typically doing multi-horizon forecasting, which means that we are predicting multiple time steps into the features. And we have the inherent challenge of increasing uncertainty. And in many applications, we would like to model also this uncertainty so that we know the range of possibilities for each predictions. And there are many different complex dynamics in real-world applications. Like here's an example where we can see the combinations of periodic fluctuations with some sudden events and some transient regime changes and so on. So we would like to propose an architecture that can handle these wide range of dynamics. And similar to TabNet, we also want to provide explainability capability, because most of the applications of time series forecasting have high desire for explainability capabilities, such as for planning or like portfolio management or medical decisions and so on. And then, as I mentioned, prediction intervals are required for special applications like risk management. So we would like to get calibrated prediction intervals when we do multi-horizon forecasting. So in TFT, we propose an architecture with the goals of end-to-end learning, high performance across wide range of regimes, and with the goal of providing time-dependent and static interpretability. And it's based on sequential processing with the layers consisting recurrent and attention-based layers, so that we can capture both the local dynamics and also long-term context successfully. And it also has some other innovations in the architecture. For example, separate processing of past observed sequences and a prior known feature sequences, integration of static features for time dependence, for conditioning time-dependent dynamics. And we have variable selection similar to TabNet for selecting of the most relevant features based on time, and also adaptive depth and complexity via component gating. So the general architecture of TFT based on these principles is shown here. So you can see that we have the past inputs, non-feature inputs, and static metadata as the inputs to the architecture. And we have first LSTM-based sequence-to-sequence encoder-decoder layers, and then multi-head attention-based time series processing layer. And we have these additional blocks in between for variable selection, normalization, and adaptive gating. And eventually, we have the decoding mechanism to obtain the forecast for all the time steps of interest. We have demonstrated the forecasting capabilities of TFT on some academic data sets, as well as some important real-world data sets, such as from finance and retail. And we have demonstrated that TFT can outperform both the traditional time series modeling methods, such as RIMA, exponential smoothing, and so on, as well as deep learning-based methods, such as DeepAR, sequence-sequence models, and so on. And this outperformance, especially compared to these traditional methods, can be quite substantial in some cases. And besides, we have interesting explainability capabilities, as I mentioned. So one of them is variable importance. So for both time-varying features and static features, we can get the importance of different variables. And here, for the example of retail sales, you can see that, for example, we have holiday dates or past sales or item number as some most important features. Then, more unique to TFT and time series data, we have the interpretability capability of visualizing persistent temporal patterns. So we have this attention mechanism, as I described, across different time steps. And this attention mechanism basically focuses on some particular time steps in the past while extracting information and doing forecasting. And this gives us insights about what past time steps are the most relevant ones for the future forecasts. For example, here we have this traffic data set, and we observe that the important time steps are located mostly 24-hour periods. And this intuitively makes sense because most traffic patterns repeat each other with 24-hour periods. And the model learns this from data from scratch. And lastly, we have the interpretable capability of in-sample regime identification. So we know what kind of past patterns the model looks at. And if we visualize these patterns and if we try to identify the regions that certain deviations occur, then it gives us insights about whether there are some sudden changes in the data generating process. And we have done this study on volatility forecasting task from finance. And we have observed that typically these periods of pattern deviations correspond to financial crisis times. And it again makes sense from financial academic literature. All right, now I will present our last project, data valuation using reinforcement learning. So this has slightly different motivations. So instead of focusing on the deep learning architecture design, in this project, our goal is to redesign the learning framework in data agnostic way. So a strong motivation for this project is that it's hard to construct large scale and high quality data sets. So if you look at the real world data sets, they are constructed in very different ways and they suffer from different problems. So sometimes we have label noise, sometimes we have input noise, sometimes the quality of the samples can be very poor, sometimes they come from different distributions and so on. And if you use naive methods on these kind of data sets, often we observe very suboptimal performance. And we would like to quantify the value of data so that we can improve the learning algorithms trained on them. And also we can improve the data collection mechanisms and we can bring human in the loop, human being the model developers in a more effective way. And in this project, we propose reinforcement learning based data valuation mechanism for this purpose. So here is the high level idea. So we have a training data set and we would like to determine the values of different samples from this training data set. And then we have these selected samples or weighted samples, and we would like to train a predictor based on it. So basically, this selector network should be trained to value the training samples in a very accurate way so that the most relevant and most valuable samples should achieve high weights. And this predictor network should be trained so that it achieves high accuracy on the target task. And this end-to-end training should be done based on the supervision we get from the target task. And the inherent challenge with this problem is that it is non-differentiable. So commonly used end-to-end gradient descent-based methods do not apply for this problem. And that's why we adapt reinforcement learning. So when we consider reinforcement learning for this problem, one major motivation is that it has some loss reward computation coming from the predictor on the target task. And we would like to use this reward as a feedback for the selector so that we update the selector to select better samples for the predictor. And we have this alternating update steps for both selector and the predictor, and eventually predictor converges to an accurate superior predictor, and the selector converges to a selector that is good at assigning appropriate values to different data samples. And this approach is designed to be model and data type agnostic, and we have demonstrated results with image, text, and tabular data. So here's a bit more detailed view, and a few important things here to note. So this data value estimator neural network, it inputs a batch of training data samples, and it outputs the selection probabilities, which are then used as an input to the sampler. And this stochastic sampling process is non-differentiable, and it selects a subset of samples from the batch of training samples. And these subset of samples are then input to the predictor, and the predictor is trained using backpropagation-based training. And eventually, we get the trained predictor model, and then we estimate its performance on the validation data. And this gives us the reward to guide the data value estimator as the feedback signal. And then we repeat this process over and over again. So a very important capability we get with our new training framework is that it opens new horizons for training with large-scale, low-quality data and small-scale, high-quality data. So let's say if we have such a data set, let's say large-scale, low-quality data might come from web crawled data or software-generated data and things like that. We can use it as the training data. And if we have a very small scale, high quality data that is constructed in some expensive way based on like group of humans and so on, then we can use it as the validation data to basically generate the reward. And this way of training mechanism is a very effective method to basically insert that high quality label information into this low quality, large scale training data set, and it eventually allows distinguishing the relevant ones from this large scale, low quality data set. So we have demonstrated this capability on a wide range of scenarios, and I will demonstrate a few of them here. So one of them is removing high, low value samples. And let me explain this scenario. So we construct a training data set so that a subset of the training data contains noisy labels. For example, here we have 20% noisy labels. And we know that if we have the perfect ordering of the values of the data samples, then removing these noisy labels should improve the performance. And if you have a very bad ranking of the data values, then removing the the highest value samples should actually hurt the performance significantly. So we demonstrate our method DVRL on this setting and compare to some of the other approaches like Data Shapley and Leave One Out and so on. And you can see that if we remove the most valuable samples, the performance degrades very quickly. And if we remove the lowest quality samples, the performance increases actually very quickly with our method. So this suggests us that our method is very good at distinguishing the low value and high value samples, and it can effectively remove the noise from the training data and improve the baseline performance. Here is the comparison of our method to some of the other methods proposed for noise robust training, and these methods are often based on meta-learning and some other complex approaches. So they have some certain scalability challenges, unlike our methods. And we have shown that we can outperform these, and we can actually get very close to clean-only data as if we knew the hypothetical labels of the noisy samples. Another application we have demonstrated is domain adaptation. And this is again a very typical scenario where we have a large-scale source data set that we use for training, and the target data set is smaller scale, but it is more relevant to the deployment scenario. So for example, the source data set might be web crawled medical data set, but the target data set is small scale, high quality clinical data set, as in this skin lesion classification example. Or the source data sets might be from emails, and target data sets might be from SMSs for spam detection task, and maybe the source data set is much larger for this, and so on. And yeah, I mean, there are very different applications of this. They can come from different credit card types, different account types, store locations, and things like that. And for this scenario, we have also demonstrated significant performance improvements over the baseline of naively training models on source data set and using them on target data sets. And with our proposed method TVRL, we can significantly improve the performance, and it also outperforms some of the other comparison models based on data Shapley, as well as we have also shown against some other domain adaptation methods. And here is an example visualization on why this capability works. So for this real-world problem, we have the problem of store sales prediction. And we have 4 different store types for this problem, and store type A, B, C, D. And our training data consists data from all these store types, whereas our target is one of them. So depending on where we deploy the model. And you can see that even if we use all of the store types during training, the model can learn how to basically overemphasize on the relevant same store type. And for example, if we are doing forecasting for store type B, then the mechanism we provide can prioritize training with samples for store type B more than the other ones, and eventually it helps outperforming naive training methods significantly. And lastly, we have also demonstrated this application of distilling the interpretable models based on high-value data. And the high-level idea is that if you want to distill a complex model, such as a neural network, into an interpretable model, such as a shallow decision tree, we know that it will be very challenging. And the inherent difficulty here is that these interpretable models have very low capacity. And because of this capacity mismatch, you typically observe underfitting if you try to distill the model on the entire data set. And instead of that, we choose the approach of, we know that some data samples are more valuable than some other ones, and we have the capability of finding the most valuable data samples for each example. So can we utilize this to select a small subset of the data that is the most valuable for each example, and then do the distillation only on the small subset of the data, so that these locally interpretable models do not underfit and they are just trained with this small subset of the data. And we have demonstrated this capability with our reinforcement learning-based data valuation framework. And we have shown that this method improves other locally interpretable models on tabular data, such as Lime and so on. And sometimes the improvement can be very significant, suggesting that this data-dependent way of separating the valuable data points can be very valuable in understanding how the model dynamics are changing based on the data, and it can be used to distill the model into some human understandable, interpretable models. All right, so that is all, and I would like to leave the remaining time for any questions you might have. And thank you. Can you speak louder?
Okay, so I have some, let's try the settings. Maybe it's better now.
Yeah, it's better.
So I have a question. So you showed this explainability. So you have an AI that says probably this or that will happen, and then you show some variables that are important. And I'm thinking that this is really cool, and for an operator, a human sitting in the other end, that's really useful. But what if you have many of these decisions? You have thousands of these decisions, and the human, I mean, the human can't keep up and inspect all of these decisions. Do
Yeah,
you have
so
any recommendations for that?
I think that it depends on the use case. So typically there are three groups of human users of explainability. So there are these model builders, data scientists who look at the explanations, and their goal is to improve basically the machine learning models, right? So I think that they can consume many explanations in systematic ways because like they might do the debugging on some particular model and next one and things like that. Then the second group is more non-technical, let's say business decision makers and so on. It might be doctors, loan officers, blah, blah. And they typically look at AI outputs, and their goal is to basically build trust on the AI outputs and interfere whenever is needed. And for these groups of people, I think a critical question is, you know that you have limited human bandwidth. So how do you prioritize what to show to them and use their time in most optimal way? I think it's a very open research and development question that we would like to also answer in practice, because in many applications, I think this will come in important ways as we deploy more and more AI models. And third one is regulators, or the like more legal bodies that want to make sure that these AI models do not violate certain principles and so on. And I think for these ones, again, it's the same question, right? They have limited bandwidth and they cannot look at all the predictions, all the models and so on. So what are the systematic ways of ensuring that these explanations make sense? So I think that for all these questions, there are some important directions, like how do we quantify the quality of explanations in systematic ways, or if you are doing human-based user studies, how do we show that with small amount of human interference, we can guarantee high quality explanations and things like that. Does it answer your question partially?
Yes, that's a very nice answer. Thank you very much.
Yeah. Any other questions?
Oh, okay. So maybe I have a follow-up question. So for example, let's zoom into the healthcare domain. Say a doctor is reading a set of medical document, like from the patients. And if our AI identify this patient has, say, two disease, right? So how can your model this based on structured data, or improve the model interpretability to help the doctors make a decision? For example, you can provide some features are more relevant that lead to this diagnosis, or
Yeah, I think, like, let's say that it is a tabular data learning problem, and the doctor is trying to make a diagnosis from hundreds of features, like a lot of medical measurements and stuff like that. So one way the doctor can use the model is the doctor will know model's decision and what kind of features the model prioritizes about that decision. So instead of looking at this entire data and trying to find all the patterns that might be beyond the human capability because we have hundreds of features, the model can highlight the most important features or the most important patterns, and the doctor can focus on it. So you can still have some doctor in the loop, but you can reduce doctors' time on making decisions significantly. It can be one way. Then another way is, I haven't talked too much about confidence here, but I think model confidence is an important aspect. So if the model can tell how confident it is for certain decision, and you can propose a mechanism that you go ask humans, doctors, only when the model is not confident, if you trust the model's confidence score. So I think that is also an important aspect of it. So basically, trusting the AI outputs whenever they are confident, and going asking humans when they are not confident, and providing explanations so that humans can look at the AI outputs in a more effective way when they need to look.
Thank you. Do we have other questions from the audience? Okay. Thank you, Dr. Arik. Yeah.
Yeah, sure. Feel free to send any other questions to
Yeah,
me.
you can. Yeah, I can stay here maybe for maybe 5 more minutes if the some other question from the audience. Yeah. Thank you.
Thank you.
Maybe I have another question. Is this part of your research, like incorporated into the auto ML product, or some other like
The TabNet
cloud
one,
AIs?
yeah, the TabNet one got productionized separately. It's actually available as a built-in algorithm on Google Cloud Platform, and we have had many users on it. The TFD one, the forecasting one, it got integrated into our forecasting platform, and it has been mainly used in retail industry, including like some of major retailers in the world. And the last one, DVRL, it is in productionization phase. We plan to launch it soon. So most of these things got integrated into some Google Cloud products.
Hello, may I ask one question?
Sure.
Sorry, my camera doesn't work well, so without
No
camera.
worries.
So I have a question about DVLR. I understand that this is a kind of extension to current model to filter out some training data set to find which one is important for training. So my question is, how long does it take additionally to check out such kind of important training data?
Yeah, so there's training complexity and inference complexity.
Mm-hmm.
So at inference, basically, we just have the predictor model. We don't need to do any additional step because we already have this trained predictor model. So it has the same complexity at inference. For training, we have the additional complexity of reinforcement learning and training of this data value estimator. So its complexity depends on the data set size and the model architecture, but typically it is a bit slower, like, I don't know, 50% to 100% and so on.
Mm-hmm.
So it is not 10 times slower, maybe at most a few times slower. And there are different ways to make it more efficient. For example, you can use similar architectures for predictor and data value estimator with some fine tuning and so on. But we have demonstrated this for large scale data sets as well. So does it answer your question?
Yes, thank you. It's very great answer.